Okay, temperature. Let's look at temperature. Okay, so what is temperature? So temperature measures the degree. So it measures the degree of hotness. So the degree of hotness, right? So it measures the degree of hotness, right, of a body. So temperature is a measure of the degree of hotness of a body, right? So we measure temperature we use a thermometer. We use a thermometer. So we use a thermometer to measure temperature, right? So there's what we call a thermometric property. So the physical property, which a thermometer, on which a thermometer depends. So the physical property on which a thermometer depends for the measurement of temperature, for the measurement of temperature is called the thermometric property. So that is the thermometric property. It's called thermometric property, right? So it's the physical property on which the thermometer depends for the measurement of temperature. It's called the thermometric property. All right. So so the working material is called the thermometric substance. So the working material is called the thermometric substance. So it's called the thermometric substance. It's called the thermometric substance, right? So we're going to look at types of thermometers. So we're going to look at different types of thermometers. So I'm just going to make a table. So let's look at, okay, so we have types of thermometers. So we're going to look at, so I'm going to put name, right? Name of thermometer. So we're going to put name of thermometer here. And then we're going to look at temperature, thermometric substance. So the other column, right? So we're going to look at thermometric substance. Thermometric substance, right? And then the other column we're going to put advantage of the thermometer. Then we're going to look at disadvantage, right? Disadvantage. Okay, so number one, the thermometer we're going to look at is the liquid in glass. So we have the liquid in glass. So we have the liquid in glass. So which can use either mercury or alcohol. So we can use either mercury or alcohol. So what is the thermometric substance, right? So it's the length, thermometric property or thermometric is the length of liquid, in the capillary tube. So that's the thermometric substance in the capillary tube. So that's the thermometric substance of a liquid in glass. So what's the advantage of a liquid in glass? So we know that the liquid in glass is those ones that we use in practicals, science practicals, and in the hospital. So those are the liquid in glass, right? So the advantage is that it is easy to use, and also we know that they are portable. So those thermometers are portable, right? So what is then the disadvantage? So since it's made of glass, right? So we know that they are fragile. So the disadvantage is that they are fragile, and also they've got a limited range. they've got a limited, since they are only for clinical use, right? So they have a limited range. So that's the disadvantage of what? Of the liquid in glass. Secondly, we want to look at the thermocouple. Thermocouple, right? Okay, so for a thermocouple, what is the thermometric substance? So it's the EMF. So it's the EMF, right, across a junction. EMF across a junction of two dissimilar wires. Of two dissimilar wires in contact with each other, right? So it's in contact with each other. So that's the thermometric substance, the EMF, right? So the advantages of a thermocouple, so it is fast response, right? Remote reading, so we get remote reading, right? Wide range, so a thermocouple is a wide range, right? So the disadvantage that we need to measure the EMFs, right? So we may need to measure very small EMFs. So we need a millivoltmeter. That's a disadvantage. Millivoltmeter needed. So that's the disadvantage. That we need a millivoltmeter. All right. So the third one we're going to look at. Okay. So we have okay. So the third thermometer that we're going to look at is the resistance thermometer. The resistance thermometer. What is the thermometric substance of a resistance thermometer? It's the resistance. So it's the resistance of a thermistor or a platinum wire, or of a thermistor or platinum wire. So that's the thermometric substance, right? So advantages of a resistance thermometer. So it is standard. So it is standard, right? It is accurate. It also has a wide range. So it is a wide range, right? So that's the advantages. Then the disadvantage of a resistance thermometer also it measures small temperature changes, right? So it measures small temperature changes. So it measures small temperature changes. So that's the advantage. So it measures small temperature changes, right? So, and then the disadvantage, it is slow to respond. So it is slow to respond, right? In other words, it's not suitable for rapidly changing temperatures, right? Okay, so the last one is the constant volume gas thermometer. So it's the constant volume gas thermometer. So I'm just going to, I'm out of space, so I'm just going to say it, right? So it's the constant volume gas thermometer. Number 4, right, is the constant volume gas thermometer. So the thermometer is pressure of an ideal gas at constant volume. So that's the thermometric substance, right? So what? It's pressure of an ideal gas at constant volume. Okay, and then the advantage is that it is standard, right? Standard. So constant volume gas is the one that is used to calibrate other thermometers. So it's a standard. It is very accurate and has a very wide range. So constant volume gas has a wide range. And the disadvantage is that it is bulky. As you see when we'll be drawing the constant volume gas, I'll show you the constant volume gas. It is bulky and it is slow to respond also. That's what you need to know. Because of the bulkiness, it becomes slow to respond, right? So let's look at temperature scales. Next, we want to look at temperature scales, right? Okay, so temperature scales. Right, so since substances change their state at fixed temperatures, right? So these can be used to define reference temperatures called fixed points, right? So since substances, right, since substances change their state, at fixed temperatures, right? Fixed temperatures. So these can be used. So we know that this can be used to define reference temperatures. To define reference temperatures. So they can be used to define the reference temperatures called fixed points, right? These are called fixed points. Right? So these fixed points, right, which can be accurately reproduced. So these fixed points can be accurately, so we can accurately reproduce them, can be accurately reproduced, right? Okay, so so we want to look at types of scales, right? So we want to look at types of scales. Number one, right, we have the Celsius scale of temperature. We have the Celsius. So we have the Celsius. So number one, we have the Celsius scale of temperature. We have the Celsius scale of temperature. Okay. So in this temperature, in this scale, there are two fixed points, right? There are two fixed points in this, right? So the first fixed point is the ice point, which is 0 degrees Celsius, right? So the ice point, what is the ice point? Is the temperature. So the ice point is the temperature of pure melting ice, right? And B, right, we have the steam point. Right? Steam point, which is 100 degrees Celsius, right? So what is the steam point? This is the temperature. So this is the temperature of steam, right? At standard. So this is the temperature of steam at standard atmospheric pressure. Standard atmospheric pressure. So that's what we mean. So, right. So if the 100 equal steps or degrees between the fixed point, so an empirical centigrade scale of temperature for a thermometer can be obtained, right? So how do we obtain that? For example, e.g., right? E.g., if the thermometric property, right, is x0, right? X0, right? X0 at ice point, right? So if we have 100 division, so x0 is ice point, and then we have x100, right? Which is what? At steam point. So x will be representing the thermometric property, right? X100 is the steam point. Then so x theta at unknown temperature. So the thermometric property at unknown temperature. At unknown temperature, theta, right? So the unknown temperature can be calculated on a centigrade scale using the equation. So this equation is what we use. It's the equation we use to calculate the unknown temperature, right? So the unknown temperature, right, theta is equal to x theta minus x0 over x100 minus x0 times 100 degrees Celsius. So times 100 degrees Celsius. So that's how we find the unknown temperature, theta. Okay. So want to look at different empirical centigrade scales, right? Want to look at different empirical centigrade scales, specific centigrade scales. First of all, we're going to start with, okay, so we're going to start with, let's say A, right? For a liquid in glass, so we're going to start with for a liquid in glass thermometer, right? So we know that theta is equal to length. Remember, for liquid in glass, we deal with length at theta minus length at 0, sorry, over length at 100 minus length at ice point times 100 degrees Celsius, right? So where want to define, right? So where L0 is equal to length of liquid thread, so L0 length of liquid thread at ice point. So that's what L0 mean, right? L100, we already defined that. So this is the length of liquid thread. So this is the length of liquid thread at steam point, right? 100, which means it is liquid at steam point, right? And then L theta is equal to, so this is the length at unknown temperature, length at, so this is the length at unknown temperature, theta. Okay, so that's for a liquid in glass, right? And then B, we're going to look at for a thermocouple, right? For a thermocouple thermometer, right? So for a thermocouple thermometer, we know that theta is equal to, what's the thermometric property for a thermocouple thermometer? So that's EMF. So it means it's EMF at theta minus EMF at 0 over EMF at 100 minus EMF at 0 times 100 degrees Celsius. Okay, so now I want to define, right, where, right, E0 is equal to EMF. So that's the EMF, right, across the junction. So the EMF across the junction at ice point. So we know that that's the EMF across the junction at ice point, right? And then E100, that is the EMF across the junction. So it's the EMF across the steam point. So this is the EMF across the junction at steam point. And then the E theta, so that's now the EMF at unknown temperature. EMF at unknown temperature. Theta. At unknown temperature, theta. Right? Exactly. So we did for a liquid in glass, and then for a thermocouple thermometer. So that's how it is, right? So now I want to continue for a resistance and then for a constant volume gas, right? And that would be C, right? So meaning C, right? For a resistance thermometer, so it's platinum. So we're doing it a platinum resistance thermometer. So we know that theta is equal to resistance at theta minus resistance at 0 over resistance at 100 minus resistance at 0 times 100 degrees Celsius. Right. So now I want to define, right, where, right, so we know that R0 is the resistance. So we know that is the resistance of the wire at ice point. So it's the resistance of the wire at ice point, right? And then we have R 100 is the resistance at steam point. The resistance of the wire at steam point, right? So it's the resistance of the wire at steam point. And then we have R theta, which is resistance at unknown temperature. Resistance at unknown temperature theta. And then lastly, right, for a constant volume gas thermometer, for a constant volume gas thermometer. So we know that theta is equal to, so it's a pressure. So it's pressure of fixed gas at constant volume, right? So the pressure at theta minus is 0 over 100 minus V0 times 100 degrees Celsius, right? So it's always, right, where, so we know that P0 is equal to, so that's pressure, right? Okay, so that's pressure at ice point. So the pressure at ice point, P100 is equal to pressure at what? At steam point. Pressure at steam point, and then P theta is equal to pressure at unknown temperature, right? Pressure at unknown temperature theta. So that's all for the 4 different types of thermometers. So that's all the temperature scales, the empirical centigrade scale of temperature for those different types of thermometers. So want to look at the thermodynamic scale of temperature. Want to look at the second scale, which is the